Now, it's still circular, so the radius of the motion is still the same. So I'm going to say R is still constant. So we're not talking about planetary motion, which is elliptical. Okay, so this doesn't apply to planetary motion. R is still constant, but V changes. And V is generally, we consider this the tangential speed. Okay, so the speed changes. Now the velocity vector changes even if it's uniform because the direction changes. We're not talking about that here. We're actually talking about a change in the speed. Everybody see the difference? So if your speed starts out at 10 meters per second and then goes up to 12 meters, 14, that's what we're talking about. Okay? So R is still constant, but the speed changes. Now I think I already showed you that the overall or total acceleration will be total is equal to square root of the radial acceleration squared plus the tangential acceleration, AT squared. Okay. And these two are perpendicular to each other. All right. So if I've got, let me make a circle here. Make a perfect circle. So here's your radial acceleration. Actually, I've got it pointing in the wrong direction. Let me go ahead and put it in the right direction here. Remember, radial acceleration is pointing toward the center of the radius of motion. Right? It's pointing there. It never gets there, but it's pointing in that direction. Okay, so this is the radial acceleration. This is the tangential acceleration. They're perpendicular to each other. All right, and because they are, we can write this out. All right. Okay, so if the tangential acceleration is not 0, that defines it as being non-uniform. It's non-uniform if that tangential acceleration is not 0. If it's not 0, then the radial acceleration is not constant. And it can either be a positive number or it could be a negative number. So if you've got a wheel going around and the friction slows that wheel down, okay, your tangential acceleration is negative, that is, it's decelerating. Okay, and your radial acceleration is also decreasing. Okay. All right. So because these are perpendicular, they can kind of be treated separately, and we can still write Newton's second law. Newton's second law still applies, right? So in the radial direction, okay, so that is a vector. That's going to be equal to the mass times the radial acceleration. So the sum of the forces in the radial direction, I should say that, is equal to the mass times the radial acceleration. But this may not be constant. So whether it's constant or not, we can still write Newton's second law for that radial component. Does that make sense? Yeah, most of the time in this course we deal with constant acceleration, but whether the acceleration is constant or not, we still have, Newton's law still applies. And for the tangential component, well, that's sub t, this, up until now, this has been 0. This sums out to be 0, but now it's not. We can write out mass times tangential acceleration. So we've got a set of we got an equation for this, and then an equation for this, and we can treat them separate. Okay. So.
So does that mean the tangential acceleration isn't constant either?
No, it can be. Yes, and generally, computing problems here it will be constant. Yeah. So it may not be constant, okay, but generally we treat it as being constant. Okay. So yeah, the tangential acceleration can be constant, just not zero. But if it's not zero, the radial acceleration is not constant. Another way of saying this is that delta A of r over delta t changes the radial acceleration with respect to change in time. This is not zero. Okay. Which is odd. We don't normally deal with situations like that in this course, but you need to be aware that they do exist. Again, an example would be I've got a wheel turning around a spoke, and it slows down because of friction and eventually stops. Okay? You've got a tangential acceleration that's negative in that case. Or if I take it, spin it, okay? Spin it up. Now the tangential acceleration is positive until I quit spinning it up. All right. Now I've got a problem here. Now this particular problem I'm going to show you is a good problem, but it doesn't involve a tangential acceleration. Tangential acceleration is actually zero for this problem. But let's look at it anyway. This is actually a pretty good problem. Can I erase this? Does everybody have this here? Okay. That way I can put it on the finally figured out how to clear objects that you put. I'm still learning how to use this board, so. Now, like I said, this problem is a uniform acceleration or uniform circular motion problem, but it's a pretty good problem. Let me put my circle back up here. So I've got here. I've got a little, like a little cart or something up there at the top. Radius r. All right, and this is vertical. All right, here's the problem. So we've got a little card or some little object that's circling around this vertical circle at constant speed. Question: what is the minimum speed required keep cart on track. So the cart circling around this vertical loop, radius r, speed is constant. So it's not slowing down as it's going up and speeding up as it's coming down. It's constant throughout. Okay, which means you're going to have to apply some sort of force to it to overcome gravity. But anyway, what is the minimum speed required to keep the cart on the track when it is right at the top of the loop? Okay. So, I'm going to give you a few minutes, and here's the approach. Draw the free body diagram for the cart. It always has, let me ask this question, it always has what force on it? We'll say it's mass in. It always has an mg force that's pointing which direction? Down. Mg is always pointing straight down. Okay, that's pretty easy for this because now it's exactly pointing straight down. So it's the free body diagram actually should be pretty easy. And then because the cart is up against the loop, okay, right, pressed up against the loop like this, there's a normal force, right? So you have a gravitational force, you got a normal force, and of course you have a centripetal acceleration. Okay, so you've got a radial acceleration, I should say, and that's the one that's going to keep it. That force is what's going to keep it on the track. Now, you want to determine the minimum speed such that when it reaches up there, it's not going to fall, but it's at the verge of falling. It's almost going to fall, but it doesn't. Okay? Make sense? So one of those force vectors is going to have to be set equal to 0. That will define the cart almost falling down, but not quite falling down. Okay, if that makes sense. Okay, start to work with that and see what you can do with it. Yeah, draw the free body diagram for the object up here. There's your object. Put all the force vectors in there. What you might want to do, you can call this the x direction, or I'm sorry, the y direction. And although down is usually negative, if you want to make down the downward direction positive, you can do that as well. Okay. Now I think you can see everything is just in this direction. You don't have any horizontal components, do you? Because it's sitting at the top. Now if it's sitting on the side, now we might be talking about some horizontal components as well. But it's sitting right at the top. This is easy, comparatively speaking. You might want to think, does this depend upon the mass? So would a heavier object have a bigger tendency to fall, or a lighter object than a lighter object? Think about that. But you can prove that though when you go through this derivation.
So when you mean fall, like I'm confused. Like
Okay, it's going up. Now it's not attached to the loop, so it's not like it's on a chain or something. The chain is moving. Okay, so you could lift it up off of the loop. What's the minimum speed it has to go so that when it's on the top, it doesn't do. Let me redraw.
Okay, so I get it now. So it's like a hot wheels.
Yeah, like Hot Wheels going through a loop. You ever played with Hot Wheels and track on the loop?
Yeah, I get it.
Okay. So what we don't want it to do is we don't want it to do this, come up here and then fall down. Okay? That's not, we want it to stay on the track, but it barely stays on. If it goes an iota slower, then it falls. Yeah, it's like a, kind of like Hot Wheels going around the loop. Except in that case, you do get, it does slow down when it goes up the loop and then speeds up. Here, it doesn't slow down or speed up. It's constant speed throughout, which is not really realistic. If you had a variable speed, that would make this a lot harder problem. And here, you're just deriving an equation. You know, well, there's no numbers to this, so it's just basically an equation. Actually pointing down. So both the gravitational force and the normal force is actually pointing in the same direction. The only thing you have countering that is the centripetal acceleration. Okay, you got two. You got one for MG, you got one for once you get those are your two force vectors. Basically, you have two force vectors. And that's, sum that up, that's not going to be equal to 0. That's going to be mass times the rate of acceleration. until you solve this. Plus, this is actually, or get AR on the side.
What did you have?